masses of supermassive black holes that reside in the center of galaxies with a new method called Very Long Baseline Interferometry with the gravity instrument at the Very Long Telescope Interferometer, or VLTI, in Chile. So, let's start by reviewing our concept of supermassive black holes, or SMBH. So, I hope we are all familiar that these are very large black holes that reside in the center of most galaxies. And what's very interesting with them is that there is apparently a relation between the growth of the central black hole at the center and the growth of the host galaxy. And despite the very large differences in the scales of the black hole at the center and the host galaxy, there is still an apparent relation between the growth. So an example of this evidence is the M-sigma relation, which shows the relationship between the black hole mass and the stellar velocity dispersion that is normally measured in the bulges of galaxies where most of their stars are found. So this is what we call the SMBH galaxy coevolution. So there is a link between the growth of the central black hole and the host galaxy. But then there are still many key questions surrounding this coevolution scenario. Like, which came first? Is it this black hole at the center or the galaxy? So it's like the chicken or the egg problem. And we also don't know how did the first supermassive black holes form. And like the M-sigma relation, there are many other scaling relations relating the growth of the host galaxy and the central black hole. So how and when did these scaling relations build up? And what are the physical processes that drive this coevolution scenario? And so in my PhD dissertation and in our team at MPE in Germany, what we are doing is we are trying to answer these questions through very long baseline interferometry with the gravity instrument. So gravity combines the light from the 4-unit telescopes, or UTs, at VLTI, which produces fringes which contain information about the observed object. One important signal that we get from interferometry observations is what we call the differential phase. Basically, this is a measure of the photocenter shift of the broadline region, or the BLR, with respect to the continuum. So if you recall your AGN unified models, so the broadline region, or the BLR, is located very close to the central black hole, and so it rotates very fast, and so it is within the gravitational potential of the central black hole. So if we can resolve the broadline region, then we can definitely measure with high precision the central black hole mass. And from this differential phase, we expect an S-shaped signal in its differential phase if the broadline region is mostly rotation dominated. So it's Keplerian, it just rotates without any inflow or outflowing signals. And with gravity plus at VLTI, there's a series of improvements in gravity, not just in the unit telescopes, but also in the gravity instrument itself. So with the all-sky coverage and extreme adaptive optics and the recent installation of the laser guide stars at the VLTI, we can now improve the sensitivity to 100-fold and the sky coverage up to 1,000-fold. So to show you some numbers, with just gravity, before the improvements, we can only observe about tens of type 1 AGNs that we could observe with gravity. But with the implementation of the improvements in Gravity Plus, we are now very excited to observe these many type 1 AGNs and hopefully measure their supermassive black hole masses. And what's exciting, it's something that I would like to share with you, is that we can now do this up to very high redshift, up to redshift 4. And this has not been done before. We are able to dynamically measure the central black hole mass of a redshift 4 quasar. So, let us start with what have we learned from the local universe. So this is some of my work that I've done in my PhD. Basically, before I entered MPE, so from 2018 to 2022, we have observed 3 low redshift type 1 AGNs. And then when I joined, what we did is we increased the sample of low redshift AGNs to 4 more targets. And then what we did is we fitted what we call the radius luminosity relation. So this is the relationship between the size of the broadline region with respect to the 51,000 angstrom luminosity. And so what we find is that using reverberation mapping techniques or RM techniques, we would expect a slope of about 0.5 in this RL relation. But then with gravity, we are seeing a much shallower slope, about 0.4. And what's the interesting thing that we could find here is that we are actually probing the much higher luminosity ranges in the RL relation that the reverberation mapping techniques cannot probe before. Because if you would observe the time lags of the light from the AGN, that's how reverberation mapping works. If you get much higher luminosities of your AGNs, you would expect that the BLR size would be larger, and therefore the time lags would be much longer. So to give you a short estimate, at about 10 to the 47 ergs per second of AGN luminosity, you need to observe an AGN by about 10 to 15 years just to measure its BLR size. We don't have time for that. For gravity, we can only do it for 2 to 3 hours. Very impressive. And as I said, we are investigating the high luminosity regime of the RL relation, which is not yet observed or investigated yet with reverberation mapping methods. And what we find is that at higher luminosities, we observe lower BLR sizes than what is expected from the previous RL relations. So my supervisor, Taro Shimizu, started investigating the same problem, but now at the cosmic noon. So for those who don't know, the cosmic noon is the peak of star formation. And as you can see, the accretion and the star formation histories also broadly coincide. So the cosmic noon, which is about redshift 2, is very interesting to see, especially in the context of the galaxy and black hole coevolution scenario. And in 2024, we published a Nature paper about the first dynamical black hole mass measurement of a quasar at redshift 2. So this quasar, which we call J0920, is about at redshift 2.3, and we were able to measure its black hole mass dynamically with just about 4 hours of observation time, which you would need about 10 to 15 years to observe this with reverberation mapping. And with some numbers here, basically we measure almost 1 order of magnitude lower black hole mass than what was expected from the 0.5 RL relation. And so if we look now, with this additional 4 new redshift 2 quasars observed in our recent observation program of high redshift AGNs, we are consistently seeing lower BLR sizes at high luminosity than what is expected from the canonical RL relation. And this is just with the addition of 4 new redshift 2 quasars. And now if we look in the context of the black hole mass versus stellar mass, our first target, J0920, is located quite below the black hole mass versus stellar mass relation. Because if you recall our recent GWST results, you would see much heavier black hole masses than stellar masses. But our 4 new redshift 2 AGNs actually lie on the same plane as that of our JWST results. So what's so special about J0920? Why is it why is it so far from the other 4? So this is an open question that we are yet to answer. And now, I'm very excited to share with you that we can also do this beyond redshift 2. So Jinyi Shangguan, our previous postdoc, who is now a professor at Kavli Institute in China, and Rick Davis, our senior scientist at MPE, has recently published at Archive their work on observing a redshift 4 quasar with gravity plus. And so this target J0529, it was observed only 5 hours during the commissioning of the adaptive optics at gravity plus. And as you can see, there is a much lower black hole mass than what was expected from the canonical RL relation. And what is very interesting here is that the differential phase here below of our J0590 J0529 rather, is not an S-shaped signal anymore. So this can only be fitted with a model of the BLR that has a conical outflow in addition to a rotating disk component. And so just to quickly explain to you what causes the shallower slope at the RL relation, so there could be two possible explanations for this. It could be possible that the SEDs of AGNs across different luminosities or redshifts may not be equivalent, as what was previously assumed when previous works are trying to deduce what could be the expected relationship between the BLR size and the AGN luminosity. Another possible explanation is that at higher luminosities, you tend to get higher accretion rates, and because of these higher accretion rates, the self-shadowing effects are stronger. That means there is an inefficient accretion at the center, which causes build-up of materials nearer to the center, and so this prevents the central radiation from reaching much farther distances, which makes us to measure much smaller flux averaged BLR sizes. And one interesting thing about our work is that we are able to observe independently the presence of outflowing BLRs through direct dynamical observations with Gravity Plus. So we are confirming what previous reverberation mapping results have found. So to conclude, we found independently our findings on BLR physics revealed by reverberation mapping results. And with Gravity Plus, we are also investigating the BLR physics at higher redshift. So just to do some advertisement, my students are also here at TPS doing different works, and I hope you can visit their posters. So thank you very much.
So it's very nice work. But so you keep measuring the smaller size for higher luminosity AGN. That's very interesting. But then, can you rule out this is not the systematics of your method or reverberation mapping, because you are actually probing at different luminosity ranges, right?
Agreed. Yes. That is something that we need to explore in our future work, because at the moment we are only limited to type 1 AGNs. So because at type 2 AGNs, it's hard to measure the interferometric signal of such AGNs. So we have a collaborator that's also doing what kind of interferometric signal would we expect from such a type 2 AGN. So yes, again, we're still limited to that. It's also possible that we are also limited because of our methods. So this is something that we are currently exploring, I would say.
Thank you very much. Very excellent talk. So I also have a question about that figure. So this LR relationship is systematically lower than expected, right?
Yeah.
And then, but when you calculate the black hole mass, this is actually consistent with other black hole masses measured by evaluation mapping.
That's a good question.
I wonder if this, how do you compare these things?
Yes, so actually no, the answer is no. So at lower BLR sizes, about this magnitude ranges, so according to our measurements, we are getting or recovering black hole masses that are about at least a magnitude order lower than what is expected from the canonical RL relation that is in this part, the dotted dark line. Yeah, so it's much lower.
Okay, thank you. Please be quick.
You mentioned it very briefly, but what would be the difference in observations in observing type 2 AGN?
So of course, since the type 2 AGNs are viewed edge on, the dusty torus is blocking the light of the broadline region and also the central AGN. So it's hard to measure the continuum and also the light from the BLR. So it will be difficult for us to disentangle what would be the light from the dusty torus versus the light from the BLR and the AGN. So that's a difficulty.
So we have to move on to the next topic. Thanks to the speaker.
Thank you.